Hi everyone, in this video we'll talk about Kruskal's algorithm for finding the minimum spanning tree in a graph. Now in the previous few videos in this playlist, we talked about Prim's algorithm for finding the minimum spanning tree in a graph. We also looked at the generic algorithmic approach for finding the minimum spanning tree, and then we showed how Prim's algorithm uses the generic approach. Now, Kruskal's algorithm is also based on the generic algorithm that we discussed earlier. The main difference between Kruskal's algorithm and Prim's algorithm is that they make different choice of cuts. Now, if you're not aware of Prim's algorithm or this generic approach, I would recommend that you watch the earlier videos in this playlist. Now, what Kruskal's algorithm does is that it grows a collection of trees. And then slowly these trees would be merged to form a single tree, which would be the minimum spanning tree. So they're a collection of trees, which is essentially a forest. And as the algorithm progresses, these trees would be joined together to form the minimum spanning tree. Now, initially in Kruskal's algorithm, the trees of the forest are just the vertices. Okay, so each vertex is a tree in itself, and that's the collection of trees. There are no edges. In each step, what the algorithm does is that it adds the cheapest edge such that it does not create a cycle. That's the main idea behind Kruskal's algorithm. And this process continues till the trees grow, and then the trees are slowly merged such that we get the minimum spanning tree. Now, as you can see, I've split the screen into two halves. On the left, I am basically going to talk about the algorithm, and on the right, we'll work out the example. So let's now understand Kruskal's algorithm. So here is the outline of the algorithm. So initially you have a set A, which is empty, and F is the set of all the edges in this graph. So A is the set of edges which form the minimum spanning tree. So initially we start with an empty set. Now, what we're going to do is you're going to choose an edge E in F of minimum weight. So all the edges that are there, you're going to choose the edge which has the minimum weight. Now, what you're going to do is we are going to check if adding this edge to A creates a cycle. So if you add this edge to A, if it creates a cycle, then we are going to discard this edge from F. Otherwise, this edge is moved from F to A. That's what is done. So Kruskal's algorithm looks at each edge of the graph, and before adding it to A, it checks if it creates a cycle in A. And then, depending on if it creates a cycle, it discards the edge. Otherwise, it adds the edge to A. Now, the algorithm stops when F is null. There are no edges remaining. And at which point, we output the minimum spanning tree, comprising of all the vertices in the graph and A, which is the set of edges which form the minimum spanning tree. So let's now apply this algorithm to this example here. So here we have a 5-node graph, and the 5 nodes are A, B, C, D, and E. And the weights of the different edges are shown. What we are going to do is we're going to apply the algorithm that we just studied. So to do that, what the algorithm does is initially the set A is empty, and that is shown here. That is initially the set A is empty. Now, the algorithm selects edges of minimum weight. So what we have done is we've ordered all these edges in terms of their weight, which is shown by E here. So E is the set of edges ordered by weight. Now, what the algorithm does, it selects the edge which has the least weight. So first, it selects DC, which is the edge with the least weight. So this edge is selected. So DC is part of the minimum spanning tree. So we have gone through this edge. Next, we look at edge AE. Now, adding AE to A does not create a cycle. So we add AE to A. So AE is also added. Next, we consider the edge AD. So as you can see, currently there are two trees that we are looking at, and it's actually a forest. Now when we look at adding AD does not also create a cycle. So we add AD to this. And as we can see that adding AD joins these two trees. The tree which just contained AE and the other tree which just contained CD into one bigger tree. So two trees have been merged. So we add AD. Now let's look at the next edge, which is ED. Now adding ED is going to create this cycle. So let's just see. So for example, here is the ED. If we add this, there is a cycle that's created. So ED is not added to the minimum spanning tree and it's just discarded. Okay. Next we look at BC. Adding BC does not create a cycle. So we add BC. So BC is also part of the minimum spanning tree and its weight is 9. Let's consider AB. Now if we add AB, we're going to do a dot. It is going to create this cycle, that is AB, BC, CD, DA. So we will not add AB here. Next, let's consider BD. If you add BD, there is a small cycle that is created, which is BC, CD, DB. Therefore, BD is also not added. So this is our A. Our complete A is CD, AE, AD, and BC. Okay, so this is how we apply Kruskal's algorithm to find the minimum spanning tree. Okay, so now that we have done this, let's just move ahead and see how we actually implement Kruskal's algorithm. All this is great, but then there are a few important things like how we find the edge with the minimum weight. How do we actually detect if adding an edge creates a cycle? So those are implementation details of this algorithm. So we'll figure out how we go about doing that. So these are the two most important questions. So first, how does the algorithm choose an edge E with minimum weight? Next, how does the algorithm check whether adding edge E to A creates a cycle? So we are going to answer these two questions next. Now, how does it choose the edge with the minimum weight? The answer is right in front of you in the example. We just sort all these edges in increasing order. Okay, so then the algorithm just walks through this order. Now, once an edge causes a cycle, it is always going to cause a cycle. So if once you detect that an edge causes a cycle, you can just throw that edge away. So this part is easy. The next question is the hard question, like how do you check for cycles? To do that, at each step, say you have two vertices U and V. Let's consider the example of A and B here. Now A and B here are part of the same tree. So if you add an edge between A and B like this, it is going to create a cycle. So if two vertices U and V are part of the same tree, then adding an edge is going to create a cycle. If U and V are not part of the same tree, then adding an edge will not create a cycle. So let's erase part of the example here to understand this one more time, because we will anyway need to erase this example because we're going to solve this again. So let's consider this case here. Now, if there are two trees here, AE and the other tree is BCD. Now, if we add an edge between A and D, that edge is permitted because it does not create a cycle, because A, the vertex A and the vertex D, these two are in different trees. So that adding that edge is possible. By the same logic, if we try to add the edge between B and D are part of the same tree. So if you add that edge, it's going to create a cycle. So we cannot add that edge. Okay. Now that's the idea of checking for cycles. Now, an internal question related to this idea is, how do you check if two vertices are part of the same tree? To do that, I'll first give you the high-level answer and then we'll look at the low-level answer. The high-level answer is we have to use a disjoint set data structure. Okay, that's the data structure that we are going to use. And all the vertices in a tree are going to be considered to be part of one set. Okay, so all vertices in one tree are going to be part of one set. So in this, so A and E are going to be part of one set. Say U1 here, U and B, C, D are going to be part of another set, say V1. Okay, so we have two sets, U1 and V1, and they are different. Now, the low-level answer to this question is the union find data structure implements this logic. So the union find data structure actually implements this. So let's study the union find data structure. So we are just going to treat the union find data structure as a black box here. And the union find data structure supports three operations on collections of disjoint sets. Okay. First is the operation is create set U, which is basically it creates a set containing a single element U. And we'll need the create set in the beginning when all the vertices are disjoint and they form trees themselves. Find set U finds a set containing the element U. So if you have a particular element U, for example, A and E are both part of this set U1, they are both part of the set. So find set A would find basically the fact that it is part of the set U1. And find set B would say that it's a part of the set V1. Okay, how we implement that, that's not something that we're going to cover in this video. Now union UV is going to merge the sets containing U and V into a common set. Okay, that's what it's going to do. So if you call merge AD, which is then, or so union AD, so if you do union AD, it is going to basically merge the two sets U1 and V1. Okay, that's what it is going to do. So this is just to give you an idea. This is not the implementation. This is not how it's actually implemented, the union data structure. But I just wanted to give you an idea of how we are going to use it. Now let's see how this is used in Kruskal's algorithm. So first, the algorithm sorts E or the edges by increasing order of weight. Okay. Then for each U in V, for each vertex U in V, you're going to call create set U. So it's going to create set U. Then for each edge in E, what you're going to do is you're going to do find set UI and find set VI. So each edge is EI has two vertices which form that set, that edge EI, UI and VI, and we are going to do find set UI and find set VI. We're going to just see if find set UI is equal to find set VI. If they are equal, that just means that it creates a cycle. They belong to the same set. They are part of the same tree. So you're not going to consider that edge. You're going to discard that. Otherwise, if find set UI and find set VI are different, what we're going to do is first add this edge to A. Then we are going to combine these two sets. So union UI VI is like you're going to combine the set of which UI is a part of with the set which VI is a part of. Basically, it's going to join the two trees. And this process is going to continue till we go through all the edges of this graph, at which point you're done with all the edges, you're going to return A, because that is basically the set of edges which form your minimum spanning tree. Okay. So now let's try to apply this algorithm to this example. Here, let's see how it works. So initially, all the edges are sorted in increasing order, as is shown in E here. Then we're going to create a separate set for each vertex. That's what creates it. So each vertex is basically a separate set. I'm just going to draw a dotted circle across each of those. So each of them is a separate set. Okay. Now we're going to consider the edges. So we are going to first consider the edge DC, because it has a weight 2. Now find set D. So what we are doing here is we're doing find set D, and we are having find set C. They're not equal, they're parts of different sets. So we are going to add, this is going to say it's not equal. Okay, therefore we are going to add DC to A. So I'm going to add DC to A. So DC is going to be added to A. And you're going to union, we have union D, comma C. So these two are going to become one set. So let's just see what happens here. So I'm just going to erase this. So this I'm going to add, because that edge is added. It's a value of 2. And these two are now part of one set. Okay. Next, we're going to consider AE. Once again, find set of A is not equal to find set of A is not equal to find set of E. It's not equal to. So you're going to add it. Okay. So that is going to be added to this set. And then you're going to union A and E. Okay. So we're going to union A and E. So this erased, and we're going to make this as one set now. Okay. Next, we're going to consider AD. Now, once again, find A, set A is going to give this set. Find set D is going to give this set, which are different. So they are not equal to that. Therefore, we are going to add AD to this, to A. And we are going to combine these two sets in the union step. So that is what is going to happen. So I'm just going to erase these. This is 5, and this will be the new set. Okay. Now we are going to look at ED. Now find set E is equal to find set D, because they're part of the same set here, this one. So you're going to just discard it. Okay. Next, we're going to consider BC. Now when we consider BC, B is in a different set, C is in a different set. B is in this set, C is in this set. Therefore, we're going to add BC. And then we're going to union it. Therefore, we're going to union this. So let's just add BC, which is 9, and then we're going to union. Now you see all the vertices have come into one set. Therefore, the next two steps, where we do find set A and find set B part of the same set, you're going to discard that edge. Similarly, when we do find set B equal to find set D, we are going to find that they're part of the same set and we're going to discard this. So this is how Kruskal's algorithm works in practice for this particular implementation. Okay, I've not talked about find set, how it is implemented. We're not going to get into those details, but at least assuming that find set is a black box which has those three different operations, which is find union is that data structure which has these three operations: create set, find set, and union. We can implement Kruskal's algorithm. Now, how much time does this take? You can see that sorting is going to take O of E times log E, because you have to sort all the edges. And then, like, the for loop is going to take O of E times log of V, and with proper implementation, it has a runtime of O of E times log E. Okay, so if you implement it properly, that's what Kruskal's algorithm's runtime is going to be. So with this, I'll conclude this video. I hope you understood Kruskal's algorithm here, and you also understood how to implement it using the union find data structure. This particular data structure, union find, and this is the algorithm for that. Thank you for watching. With this, I'll conclude this video.